Today we're talking about solving these inequalities with rationals. And so let's do a quick review of rationals and what they look like, and then some basic practice on creating a single fraction out of the two. So let's start off with what we mean by rational. So that's really a way of describing a fraction. So 1/2 or 2/3, those are rational numbers. Also 5/1 or 10/1, those are rational numbers. But what's unique here is when we have a fraction and the denominator has a variable in it, because that means there are certain domain restrictions. That means there are certain numbers that you can't plug in and get an answer out. So for example, you could plug in a 1, you could plug in a -1, but what if you plug in a 0 on this parent function? So that's going to create a situation where we have a spot on the graph where there is no point to plot, and so I cannot plot at 0. So we use a vertical asymptote here to represent the fact that nothing exists right there. And this creates two separate branches. We'll be doing more work with these in the future, but for now, notice that some of the graph is under the x-axis and some is above the x-axis. And so with the inequalities, we're always asking the question, are we above or below the x-axis? To take it a step farther, we want to identify where we have the graph, or any feature of the graph, crossing that x-axis, because that will create some critical values. Right now, we have the vertical asymptote that is crossing the x-axis. That's a critical value right there at 0, because that means it's a division between one interval and the other interval. But if we have other graphs, other equations of this graph which might involve, say, like a vertical shift or a horizontal shift, notice that what happens is now that you have a part of the branch creating an x-intercept and the vertical asymptote, which is creating a point that's a critical value, but it's not an x-intercept itself. So that means you can have pieces of a branch that are above, or the entire branch that is above the x-axis. You can have pieces of a branch that are below the x-axis, and in some problems you can even have multiple vertical asymptotes, and that means you just have more branches in a variety of places. So I'm just kind of making this up here, but maybe you have something like this. You have 3 separate branches, right? And if you have a vertical shift and like a horizontal shift, notice that we end up crossing the x-axis in several places. So that's going to create lots of intervals that we then have to test. So that's just an overview of the function of that vertical asymptote and what it's doing to the branches here. So we'll be finding those critical values in a moment. You see the boxes down there that describe that. We'll get to that shortly. Let's just take a moment and review how to combine these into a single fraction, because in order for us to find those critical values, we need a single fraction. So you might remember we need to create a common denominator, and we do that by multiplying top and bottom of the fraction by whatever we need to create a common denominator. So here we have a 2/x plus 3x/x. Now we have the common denominator. So that means we can add the numerators over that common denominator of x. Now here's a follow-up question you need to consider. Take a look right here. You have an x on the top and an x on the bottom. Should we simplify the fraction? Can we cancel out those x's? And the answer is no, we cannot. Don't do that, because remember, the division bar is a type of grouping symbol. That means you have a binomial. You have to treat this as a bundle. You can't pick and choose some terms to cancel out and ignore the others. You either have to cancel out every single term or none at all. So this cannot be reduced. Same with what you see here in part B. You have an x plus 5 over x minus 3. Can you cancel out those x's because you have an x on top and an x on the bottom? Certainly not, because you have a binomial, and that's understood with the division bar. Okay, we have a 4, which is a 4/1. That means we need to set up a multiplier and identify the other denominator, which is x minus 3, and we'll use that as our multiplier above and below. So here's the first fraction here. You want to think of this as not just a 4 that's being distributed, but you want to think of this as a negative 4 that's being distributed. So negative 4 times x and negative 4 times negative 3. So watch out for your signs right there. And when you do that, you might say, wait a minute, what happened to that sign in the middle? Well, what we're doing is we're combining them. And when you add a negative, that's the same thing as just subtracting. So we just reposition the subtraction sign here above by distributing it. So now with a common denominator of x minus 3, we have all 4 terms on the top. We have an x, a positive 5, a negative 4x, and a positive 12. So now we'll combine those like terms. We end up with negative 3x and plus 17 over that x minus 3. Again, you might be tempted to say, hey, there's an x above and below. I can cancel those out, right? No, you cannot. You'd have to cancel every single term the same way. Here for this third fraction, we have 2 different denominators. One is an x minus 3, the other is an x plus 3. So we'll take each denominator and multiply it to the other. So in the first fraction, what's missing is the x plus 3. So we'll multiply top and bottom with that x plus 3. On the right fraction, we already have the x plus 3. What we're missing is the x minus 3. So we'll multiply top and bottom by x minus 3. So we have a 5 to distribute to its binomial. We have a 3 to distribute to its binomial. So we have a 5 times x plus 15. And we have a 3 times x minus 9. And that's over a common denominator of. Now we're not going to FOIL these together. We're going to leave those factors side by side because it'll be easier in the work we're doing today to find those critical values. So we'll just combine the like terms on the top. So we have an 8x plus 6 over that x plus 3 times x minus 3. So there's a quick review on simplifying our fractions into a single fraction. That's what we'll have to do with our first step in these problems. Now, as we'll have an inequality, the problem will actually have either a less than sign or a greater than sign, and we'll be comparing it to 0. So what we want to do is to find these critical values. For the numerator, we'll take the numerator apart from the denominator. We'll take the numerator, we'll set it equal to 0. We'll solve for x. And any values you get, these are the x-intercepts. We'll use either the rounded or the square brackets depending on the inequality symbol. For the denominator, we'll set the denominator equal to 0 and we'll solve for x. This is not an x. This is not an x-intercept. This is a vertical asymptote. So that means there is no point that exists there. No part of the graph exists there. So we cannot use the square brackets. We're only using the rounded brackets. Let's do 2 examples on the next page here. I'm going to look at example 1 and example 3. So on this first example, this is actually the same setup as what we saw on the previous page with part A, creating a common denominator. We are having this inequality of less than 0. So the question is, where does this graph to be found? Over what interval will the graph be underneath the x-axis? So setting up my multiplier of x over x, like what we did previously, we will find ourselves eventually at 2 plus 3x over that common denominator of x. Where is that less than 0? So this is the real problem that we have to solve. That's the format that we need. So step 1, we're going to find those critical values. To do so, we're going to look at the numerator and the denominator separately from each other. We'll take the numerator and set it equal to x, equal to 0, and solve for x. And this will give us an x-intercept. So that's where one of the branches is crossing the x-axis. We'll take the denominator, set it equal to 0, and solve as well. So that's already isolated. So that's not an x-intercept, that's a vertical asymptote. So I like to think about what kind of bracketing system I need. I need rounded brackets around the 0, and because of the less than sign, I need rounded brackets around the negative 2/3. So when I set up my table for the intervals, I am going to be using those rounded brackets around those numbers. So here's the test interval chart. So I have an interval from negative infinity to negative 2/3. We have an interval from negative 2/3 to 0. And lastly, from 0 to positive infinity. All right, where did that come from? I recommend we always draw this little number line that goes from negative to positive infinity, just to order our values from smallest to biggest, and that way we can pair up these two at a time. So we have an interval on the left, one in the middle, one on the right, and so you can see how we found the pairing of each of those values. Now we want to find a test value. We're picking any number we want as long as it's between these two numbers. So don't pick negative infinity, don't pick negative 2/3. How about negative 1? All right, so we'll use a negative 1. How about something between negative 2/3 and a 0? So how about a negative 0.5? And then how about a value of 1 for the remaining interval? We're going to take each of those and plug them into this simplified fraction. So 2 plus 3 times that input of negative 1 over the input of negative 1. We want to see whether that gives us a positive or negative result, and that happens to give us a positive 1. Here we have 2 plus 3 times that input of negative 0.5 all over an input of negative 0.5. So this gives us a result of negative 1. And for the third test value, we have 2 plus 3 times the input of positive 1 over an input of positive 1. So that'll give us a result of positive 5. We're interpreting these results now by asking the question, which of them are less than 0? So only that middle result. And that came from this interval. So this is the solution interval. This is the only place we will find on the graph that is underneath the x-axis. So my solution interval is going to be negative 2/3 to 0. So that's the answer. All right, so let's take a look at one more example. We'll go down to example number 3. Again, we have to have a single fraction, and we actually have two separate fractions. So we have to bring that 3 to the left-hand side and then create a common denominator. So I'm going to subtract 3 from both sides. So we have less than or equal to 0. And then we want to multiply that 3 by x minus 5 over x minus 5. And remember to keep that negative with the 3 when you distribute to the binomial. So we have 2x minus 7 over x minus 5. Here we have a negative 3 times x and a negative 3 times a negative 5 over a common denominator of x minus 5. So what happened here in the middle? That's a plus sign, because adding a negative is the same as subtracting. So we have, over that common denominator of x minus 5, we have a 2x minus 3x for a negative x, and a negative 7 plus 15 for a positive 8. So that is going to be set less than or equal to 0. So that's what we're trying to work with there. So to find our critical values, we'll separate the numerator from the denominator, setting each of them equal to 0. So the numerator is that negative x plus 8. Set that equal to 0. And here you can see that the x is actually negative, so I'm just going to push it to the other side. Let's add x to both sides. So 8 on the left, positive x on the right. For the denominator, that's an x minus 5. Set that equal to 0. Isolate the variable. So these are the two critical values. And think about the brackets now. For the denominator, we always use the rounded brackets. And for the numerator, we use either rounded or the square brackets, depending on this inequality symbol. So it's less than or equal to, so we want the square brackets around the 8 whenever we use the 8. So here's our table for the test values, or the test intervals. Using my number line here to help me organize my information from smallest to biggest. We'll have a 5 and then an 8. So we have intervals from negative infinity to 5, rounded bracket, from 5 to 8, square bracket, and then 8 to positive infinity. So I want to pick some test values here. So I'm going to start with that first interval, picking a test value of 0, because that's between the negative infinity and 5. Here, something between 5 and 8. How about a 6? I'll pick 6, and then something between 8 and infinity, I'll pick a 9. Take each of those, and we're going to plug them back into this fraction. So we want negative 0 plus 8 over 0 minus 5. So that simplifies to a negative 8 fifths. Now plug in the 6, so negative 6 plus 8 over 6 minus 5. That gives us a result of positive 2 over 1. And lastly, plugging in the 9. So negative 9 plus 8 over 9 minus 5. And that gives us a result of negative 1 over 4. So we're interpreting those results to see which of them are less than 0. So that gives us the first and the third. So our solution intervals will be these two, negative infinity to 5 in union with 8 to infinity. That's where we will find the graph underneath the x-axis. Here, that middle interval, then in fact would be part of the graph that would be found above the x-axis.